Welcome to Fred
and Amy's Math
Math
Shack.
Hi, today I'm going to introduce inequalities. We're going to look at linear inequalities, then we're going to look at some slightly trickier ones and some notation that goes with it before quadratic inequalities appear. So to start today, try these two questions out and think for the second one what two solution methods there might be, because there's two that you would commonly see for this type of inequality. Hopefully you've given that a go. The first one, this will be my solution method. Minus x from both sides, minus 1 from both sides, and then divide by 2. We solve them a bit like equations. Why do we do that? Because I've got here sort of some unbalanced scales, really, some weighing scales. But if I do the same thing to both sides, they'll remain unbalanced in the same kind of way. That's the best explanation of it. So we can still treat it a bit like an equation, although you need to be careful. There are times when that falls apart, as we'll see. For this one, if you solve it the similar kind of way to there, then actually it's this solution here. You would add x to both sides and then add 5 before dividing through by 3 and rewriting it as x less than or equal to 2. The second method is actually to minus 2x from both sides, minus 1. And at this point, you actually, when you divide through by minus 3, you have to change the inequality sign around. So you can see it switching around. Now it's consistent with the first, this solution method that I gave. And essentially it's a key fact to remember. When you times or divide by a negative, you have to swap the inequality sign around. Here's a little bit of an explanation of why. If you're comparing two numbers, say minus 2 and 4, we can see that minus 2 is less than 4. If we divide through by negative, then the whole number line kind of is reflected essentially. And we can no longer say that 2 is less than minus 4. So we have to swap the inequality sign around for it to make sense. Let's look at a few other scenarios where you may or may not have to swap the sign around. So I'll read this carefully. Which of the following operations causes an inequality to remain true without having to change the inequality sign? So multiplying or dividing by a negative is never true. You always have to change the sign around. And let me give you an example. I'll put my examples down here. Just feel free to write outside the box. If we have minus 2 is less than 3, then if I multiply or divide by a negative, say minus 1, it would become 2 and minus 3. I have to swap the sign around for it to make any sense. The same would go for two positive numbers, but that's one example. Okay, so think about the other ones. Will you have to swap the sign around? Will you have to keep the sign the same, or will it depend? Here is the answer. So if you're multiplying or dividing by a positive, I'll put this as example 2, you don't need to swap the sign around. So 2 is less than 4. If I double them both, I get 4 is less than 8. And the same would be true for, say, minus 4 less than minus 2. We'll get minus 8 is less than minus 4, and all is good. So we always keep it the same. Adding a positive, it's very similar. This would just, if I added 1 to both of these, it would be 3 is less than 5, and it would stay the same. The same would be true because on the number line, we're just moving up or down the number line. It's when you times and divide by negative, you get this sort of reflection going on that I spoke about. Subtracting a positive, same thing. Adding a negative is the same as subtracting a positive. And this one here, subtracting a negative, is the same as adding a positive. So they're all linked together. They're basically just adding and subtracting. So I want to focus on squaring both sides. Let's look at an example for this. So example 3, we see that 2 squared is less than 3 squared because 4 is less than 9. If I rushed that a bit. 2 is less than 3. Let's start that again. Okay, we see that 2 is less than 3, and if we square both sides, we get that 4 is less than 9. We don't swap the sign around. However, if I go with minus 5 is less than 1, if I square both sides, I get 25 is greater than 1. and I have to swap it around. So really, I would avoid squaring with inequalities wherever possible. There are times when you might be able to, but you'd have to think about whether they're positive or negative, essentially. So just be aware. Taking a reciprocal means making it 1 over. So if you had something, I'm running out of space here, but if you had that a half is greater than a third, if you take the reciprocal, that means 1 over, so you get 2 and 3. And actually 2 is less than 3, you'd have to swap the sign around. However, if you had, this is my last example over here, if I had that minus a half is less than 4, if I take the reciprocal, I'd get minus 2 is less than a quarter, and I'd keep the sign the same. So again, basically, try and avoid ever taking reciprocals with inequalities or square rooting. If you need to, then you need to think about it more deeply than just swapping the sign around. You need to think about specific cases. Right, there's one other thing to bring about with inequalities, and that is notation. This is typically how we would write down some different solutions to equations. Okay, these being the most common here, these may be a bit different, you might have encountered them. Now there are two other types of notation that you need to be familiar with, and I'm going to talk you through them and then test you on them. There's something known as set notation, and let me just show you. Set notation is when you say that you've got the set of x, and this little dot dot here means such that. So I would read this as the set of x such that minus 2 is less than x less than 4, and then I'd end the set. You might think that's overcomplicating it, but there are reasons you see it, and it's just, set theory itself is a branch of mathematics where you'd see this sort of thing, so you're just expected to have some familiarity with it here. There's then a really nice bit of notation, which is, because that is, in some ways, this is less concise than this, because I'm having to write more. Interval notation is more concise. This would be my answer here. It's not a coordinate, it is me saying that x is minus 2 is less than x, which is less than 4. That's what these brackets actually indicate. And you'll see as I do more examples how it all comes together. For this one then, it's very similar. It's just that now I've got the inequality signs, including 7 and 19. Interval notation looks like this. Because I want to include the value now, I use square brackets on the left and square brackets on the right. Here's one more for you to look at. How do you write down x less than or equal to 5? Well, this one is very similar, just with set notation. This one here, we introduce minus infinity into things. So we're saying everything is between minus infinity and 5. It can include 5. It can include minus infinity because we can never get to minus infinity. Always put a bracket like this around infinity or minus infinity. So now I've said that, I want you to think about the answers to the rest of them. Think about this one and then I'll go through it and so on. But do have a go yourselves rather than just watching me do lots more examples. Okay, this one, very similar. And then now, this is going to be very similar again, but I don't include the zeros, so there's a normal bracket. Here, you guessed it, it's going to be that. And for this one, I have 8 on the left now. I'm basically saying that 8 is my lowest number, but it doesn't include it. And it goes all the way up to infinity, but I can't include infinity either. And then this one here, that should have been, sorry, there's a typo. That should be a 3. I rushed that, didn't I? And then this one is 3, but we include 3 up to infinity. Okay, slightly, this is why, you'll get a bit more understanding of set notation with this. Okay, if we're doing or in words, then when we do set notation, we use this symbol. It means or, it also means union. It's the union of two sets. I'm not going to talk about a lot about that, but that would be how you'd write it. Very, it looks very complicated, but it means exactly the same as that. But if you're trying to remove words, then this is a way of doing it. This is really concise with interval notation. You just write your two intervals and then union. Meanwhile, for and, you would write it like this. This means and or intersection. I'll write that down in a second. In this case, if I'm interested in x being between 2 and 7, but also greater or equal to 6, then it can't actually be 3 because that doesn't obey that one. So I can in fact bring it together into a single inequality. It will have to be greater or equal to 6, but less than 7. You could use a number line to figure this out. So if we have 2 and 7 and 6, I'll just draw a bit of the number line. Then my first set of solutions is this, and you may remember that we put little circles to show that we're not going to include the value. And then my second set of solutions is this, with a arrow going that way and a filled in circle. So I'm basically interested in where the overlap is, and the overlap is going to be this to here. So I'm just trying to explain where that has come from. Interval notation becomes this, which you would simplify to that thing on the right. So just to say again, that symbol means intersection. It is where two sets intersect. Also, and is what it means. Finally, for no solutions, here we go. You get this symbol here, which I believe is it in the Norwegian or alphabet, or in some other Scandinavian countries' alphabets, and it means empty set. You can just use that symbol to indicate it. Okay, hopefully you're happy with that. Some new types of notation for inequalities. So let me test you on this a little bit further. What would be, do you know what? Let's do both. What's set notation and interval notation for this one? Let's do set notation first. Okay, it's going to be the set of x such that minus 3 less than x less than or equal to 6. We'll come back to interval notation. How about this one? Actually, I'm just going to show you all of them. This one, set of x such that, it's important to think through what each symbol means as you do it. So I'm explaining it as I go, what I'm writing. Set of x such that x is less than minus 5. Here, set of x such that x is less than or equal to minus 8, unioned with the set of x such that x greater than 10. This one, set of x such that 7 less than or equal to x less than or equal to 19. And here, set of x such that x greater or equal to 9. So in some ways, this one is the easiest one to do if you just got to remember the sets bit and the such that bit. Interval notation then, we're going to get bracket minus 3 comma 6 square bracket. Here, minus infinity, normal bracket, comma, minus 5, normal bracket. This one is going to become minus infinity, comma, 8 square bracket, unioned, normal bracket, 10 bracket, infinity. This one's not too bad. It's going to be square bracket 7, comma 19. And finally, 9 with a square bracket, comma infinity. Let's look at a few more questions on linear inequalities. Find the set of values of x for which these are true. Okay, you can pause the video. I can and try them, or watch me do a few and then try some. Up to you. Leave your answer in any of the three notations. I'm not too worried about that. I'm just going to leave it in the simplest one, the one that you get from solving the equation before you. I don't actually know the name of it. The set notation, interval notation, and just sort of your normal notation, I suppose. This first one, multiply the bracket. 3x plus 15 is greater than 5 minus 2x plus 20. Add 2x onto both sides, so it becomes 5x minus 15 from both sides. 5x is greater than 10, so x is greater than 2. Here we encounter one where we've got two inequality signs, but it's okay because we can just do the same thing to all, like it's as if we've got three sides now, so we can minus 1 from both sides, and then we can divide everything through by 3. Nicely done. However, this fails here because I've got x's on all three, and you can't eliminate it so that you just get a single x. That's the issue. So for this sort of question, split it up into two inequalities. First of all, the 2 on the left, and then the 2 on the right. So we're going to get that 2x is greater than 2, x greater than 1. Now look at the second 2. We're going to get that 3x is less than 6, so x is less than 2. And actually, overall, we can bring this together. Minus 1 is less than x, but less than 2. Okay, try this one in a similar way. First 2. It's going to give me 4x. We're going to get 4 and minus 4 less than 4x. X greater than minus 1. And then here, I'm going to get 3x less than 9, so x less than 3. And overall, minus 1 less than x less than 3. Brilliant. We got one more type of inequality to look at, and these are quadratic inequalities. So I've actually already factorized the quadratics, and that is going to be the solution method. Just like when we solve a quadratic, we try to factorize it, or use the formula, or we complete the square. We can here try and factorize as well. Because why would we want to do that? Well, actually, we're going to return to the idea of sketching a quadratic. So let's imagine I set y equal to the expression on the left, and I try and sketch it. I would get intersection points minus 2 and 1. And my quadratic would look a bit like this. Because now if I say to you, where is this function y equals this thing on the left less than or equal to 0? Well, the function is less than or equal to 0 here, because it's below the x-axis. So if I want to work out the values of x, they're going to be here. And I can simply write down that minus 2 is less than or equal to x, because I'm including equal to 0, which is less than or equal to 1. And I've solved a quadratic inequality. So the process is, get it factorized, it already is in this case, draw a sketch of it if it was y equals that thing. With the roots on, I'm not interested in the y-intercept. Look for where it's less than or equal to 0, or greater than 0 in this case over here, and then work out the range of x. Okay, try this one yourselves. It's going to be very similar. So I'm going to get minus 3 as a root, and then actually 2x plus 5 equals 0 is another one. That's going to be x is minus 5 over 2, or 2.5. So actually that's going to go on the left as well. It might be best to just redraw this. So minus 3 minus 5 over 2. I'm going to get a quadratic that comes down like this. Now, this time I'm interested in where it's greater than 0. So let's look at where the quadratic is greater than 0. This time it's here, and it's here. And my x values are going to be everything this way and everything this way. So I'm going to get x is less than minus 3, or x is greater than minus 5 over 2. I don't try and write it as a single quadratic. It's a kind of a union one. So two different scenarios. Have a go at these. There's an extra step now. I'm giving you the quadratic, so you first of all have to factorize it. The first one factorizes as follows. So we get minus 2 and 3. Where is it less than 0? Less than 0 here, which gives us these x values. Brilliant. Right, this last one. Okay, there's a few ways you can do this. My advice would be to actually rearrange this so it's 2x squared plus 5x minus 3 is greater than 0. So actually I've equivalently times through by minus 1 and swap the sign around. This is a negative quadratic on the left if you were to sketch it, but I've kind of turned it, I've made it happy, I've turned it into a happy quadratic, and I can solve it in the same kind of way. I'll talk a little bit more at the end about how we could draw it as a negative quadratic, but I've turned it into a problem that we can now deal with. So this is going to factorize. Well, hopefully it will. Let's try it. Okay, there's not lots of numbers to try. I think it's going to become plus 3 and minus 1. Get this from trying some out. There's only two options really, 1 here and 3 here, so I just realized the 3 had to be over here. Okay, let's get our sketch down. This is all assuming that you're familiar with sketching and you're confident with it. Otherwise, please look back at that. It's not a focus today to talk about that. I just put that in the wrong place. So that should be minus, let's do it again. Minus 3 as a root and a half as a root. Where is it greater than 0? Here and here. So x values here and here. X less than minus 3, or x greater than a half. Now that's the way I want you to solve these, with a non-calculator method, essentially trying to factorize. Like, that's good maths, but I do want to tell you that you do have your Classworks calculator, and it can be used as a check. I want you to treat these questions as if I say, like, show all your workings. I don't just want the answer, I wanted the working as well, but you can check your answer. If you go back to here, we've used equations and functions before, but there's this inequality one as well. You can actually solve quadratic inequalities. And then you can type it in. So this one is a less than 0, 1. And then put it in. 3 minus 5 minus, wait, I put it in the wrong way around. So that should actually be minus 2. Easily done. Minus 5 and 3. Press equals, and it gives you the solution straight away. So do be aware of that. Just want to quickly talk about how I could have sketched the graph. Like if I found out the roots were a half and minus 3, maybe I used the quadratic formula, then I could have looked at the original one and put those roots in and then drawn like a sad quadratic essentially, and then looked where it's less than 0. So I just want to show you that I would have got exactly the same answer. It would be the branches here and here. But personally, I would always turn it into a happy quadratic. Just be aware, just be careful, because it's easier to factorize a happy quadratic. That's the point I'm trying to make. Right, one more. Give this a go. Notice in part B I've said you must show all your working clearly. Okay, when we are told that a quadratic has 2 real roots, the thing that needs to be jumping out of us is the discriminant. What's going to happen with that? Remember, 2 equal roots, it's equal to 0. No real roots, it's less than 0. So obviously that could come into quadratic inequalities, but here, 2 real roots. 2 real roots. Well, actually, technically, that could be 2. Let's change it to 2 distinct real roots, because that's what the question wants. So then b squared minus 4ac is going to be greater than 0. Okay, and then I can look at it, and this bit, this is a, this is b, and this is c. So it's going to be minus m plus 3 squared, which is just the same as m plus 3 squared, because you can ignore that negative. Minus 4 times 3m times m minus 2, and that is going to be greater than 0. We formed an equation. We now need to basically simplify it to this thing here. We're going to get m squared plus 6m. I'm doing cross multiplication of 3m twice, plus 9, and then minus 12m m minus 2. I've just decided not to rush that bit. M squared plus 6m plus 9 minus 12m squared plus 24m greater than 0, minus 11m squared plus 30m plus 9. Like, try not to, like, you can use the answer as a guide. If you didn't get minus 11, I'd straight away be looking back here. But they are the same, these two. We just need to flip the sign around. So it becomes 11m squared minus 30m minus 9 is less than 0. And we're done. Solve it, finding the possible values of m. I'm going to do it by factorizing. Okay, it is an awkward one, but it's not that awkward because the only thing that it can factorize is 11 and m, because 11 is a prime number. And then one of them is going to be negative and one of them positive, for this to be minus 9. So if I put 3 here and 3 here, I see that I get 33m and 3m. So to make it work, I make this minus and this plus. Okay, that is the factorized quadratic. We then draw a sketch. 3, and it's going to be minus 3 over 11. Where is it less than 0? Here. Let me try again, that was really very good, was it? There we go, it's better. So between these values, so minus 3 over 11, less than x, less than 3. Okay, fantastic. Well done on your efforts. We've done a lot on inequalities. You know, we have spent a bit of time revising linear ones. Talked about the rules. You might not have been aware of these before. You might have never tried to take the reciprocal of inequalities, but just be aware we've introduced notation, introduced these ones here that are a little bit sneaky, and then brought back, you might not have ever seen them before, quadratic inequalities, even introducing their discriminant into it. So we've done a lot. Well done.